Okay, finishing up from class, because we ran out of time a little bit. I now have a polynomial f of x equals x cubed plus 3x squared minus 18x minus 40. And we want to find the roots of this thing. Now previously we would just do blind guessing using the law of ones as a guide. But now we can do a little bit better because we know by looking at the leading coefficient and the final coefficient that if f has a rational root, then that rational root has to be of a form in which the denominator is a factor of the leading coefficient, and the numerator is a factor of the constant term. So, what are the possible rational roots of this polynomial? Well, the denominator has to be a factor of the leading coefficient, but the leading coefficient is just 1. And the numerator has to be a factor of 40, so that's 2, 5, also 1, I guess, 2, 5, 8, 20, 10, and 4, and 40 itself. Okay, and then let's not forget that there are also all the negatives. So now there's 1, 2, 3, 4, 5, 6, 7, 8, 16 possible rational roots. And that's it. So we used to start guessing wildly and just keep guessing and guessing and guessing forever. But now we've narrowed it down to 16 only possible numbers to check. So I try 1. So 1, 3, negative 18, negative 40. I try 1, does that work? Well, 4, negative 14, negative 14, negative 54. It doesn't work. And I can try negative 1, and I can try 2, and I can try forever. So I have only 16 of these to check. And if all 16 of these don't work, then this indeed has no rational roots. On a hunch, I will try 2. Let's see if that works. Actually, I'm not sure if it does. 10, negative 8, nope, it doesn't. Negative 2, I think I'll try. So 1, negative 2, that gives me a 1 here. That gives me negative 2, so negative 20, so that's 40, and in fact, negative 2 is a root. Okay, so that's pretty exciting. And then, if you give me something more complicated like this, now I look at the possible rational roots here, and I see that the numerator must be a factor of the constant term, so that's 1, 5, 25, and the denominator must be a factor of 1 and 3. So I have 1, 2, 3, 4, 5, 6 combinations, plus the negative, so there are 12 possible roots. And I can try all of them, and if I try 1 and it doesn't work, and it doesn't by the way, and I try negative 1 and it also doesn't work, normally I would go on and I would try 2. But now I don't have to try 2 because I know that 2 cannot possibly be a root, because 2 is a rational number, and the only possible rational roots must be of one of these forms. So I get to skip 2 and go on to try something else. Anyway, find the rational. This function does have a rational root, I promise. Find it, and then that's the rational root theorem. Okay, bye.